Hello students, good day. In the previous couple of sessions, we discussed how processes are managed by the operating system, how a process moves through various stages through its life cycle, what is a ready state, what is a running state, and what is a waiting state. So we saw that a process can be in the ready state, meaning that it is waiting for the processor to be allocated to it. Then it can be in the running state where where the processor has been allocated to it, or it can be in the waiting state where it is blocked for some IO operation. So our today's discussion is in a way an extension of the same process management. Over here we will discuss about what happens when there are multiple processes in the ready queue and how operating system pick one of them and passes it to the processor. So the selection criteria of selecting a process out of multiple processes waiting for the CPU time is discussed in this session. Today we will talk about how an operating system should select a process from multiple processes. What should be the defined criteria for this selection? So the first criterion for this selection is to maximize the CPU usage. So the maximization of CPU usage can be the very first thing for the selection of processes from the ready queue. So based on this, to maximize the CPU usage, operating system switches among multiple processes to ensure that there is time sharing, and to ensure that if a process is busy in performing some other job, still CPU can be utilized by other processes. Usually, process scheduler is a component of the operating system that selects which process should be taken out from the ready queue and being passed to the processor. Usually, to perform such tasks, there are various queues that are maintained by the operating system. The first of them is the job queue. This queue maintains all the processes that are still running in the system. By running over here, I mean that they are waiting for the execution or blocked for some IO, but they are active processes. The next queue that operating system maintains is the ready queue, and these are all the processes that are sitting in the main memory, and they are ready, and they are not occupied somewhere anywhere else, and they are just waiting for their turn to get executed in the processor. And then we have a device queue. We have multiple queues for each of the devices, and over here we have the set of processes that are waiting for that particular IO device to complete its operation. And during its life cycle, one process may move through all of these queues, or multiple queues throughout its life. Over here we have the visualization of the same concept. You can see that this is the CPU, and it processes all the processes that are coming to it, and this is the ready queue maintained for all the processes that are ready to get executed in the CPU. And then over here we have multiple queues that are waiting in different stages and waiting for different things to complete in order to go back to the ready queue. And over here we have our scheduling task out of multiple processes waiting over here, or operating system scheduler selects one of them and passes us on to the CPU. There are two basic types of schedulers. The first one is long-term scheduler, which is responsible that when a user selects a program to execute it, the long-term scheduler finds out whether we have enough resources in the system, and whether the execution of this process may not harm the whole environment of the system. So this is the scheduler that selects how many processes should be running in the system at any point in time. So in a way, This scheduler selects the degree of multi-programming, that how many multiple programs can be running in the system at any given time. The second type of scheduler is the short-term scheduler. This is the particular scheduler we were talking about a while ago. And the responsibility of this scheduler is to select a process from the ready queue and pass it on to the processor. So this scheduler has a criteria, well-defined criteria, and based on that, it selects a process and and let it continue its execution in the processor. Sometimes this is the only type of scheduler that is present in the system, and the difference between this long term and short term is one is at the probably entry gate, and the second one is the one who is moving these around from the ready queue to the processor and vice versa. This short-term scheduler, it is invoked quite frequently because whenever we have an expiry of time slot, we have to select another process from the ready queue. However, long-term scheduler is invoked not with such frequency, and because it is only invoked when the user selects to execute a process. So short-term scheduler is our main focus over here, that how can we select a particular process from a set of processes and passes it on to the processor. As we have already discussed that there are two types of processes. One is the IO bound processes and the other one is CPU bound processes. IO bound processes are the ones that spend most of their time doing the input output operations rather than the actual computations in the processor. So most of the times they are involved with the input and output devices, and they only spend small chunks in the CPU. An example of such type of processes is your browser, where most of the times it is involved in the input and output, while only some time is spent for the actual CPU processing. The other type of processes are the CPU bound processes, and these are the processes that spend most of their time during the computations, and only few times they may involve in the input and output operation. It's a responsibility of the long-term scheduler to find a good mix between these two types of processes so that the system is not loaded in a bad manner. Along with different types of schedulers as well as processes, now we will discuss that there are different types of process scheduling as well. There are two types. The first one is primitive process scheduling and the other one is non-primitive process scheduling. In the primitive type, once the time slice of the processor expires, whatever process is running in the processor, it is taken out by the scheduler and returns it back to the ready queue, where this process waits along with the other processes for the scheduler to pick any other process one more time and pass it on to the processor. Uh, in this primitive type, it is not necessary for a process to complete its execution whether we are more dependent on the expiry of the time slice of the processor. In the non-primitive type, once a process gets the processor, the scheduler cannot take it out and it remains in there for the whole duration of its execution. So once a process gets the CPU time, it remains in there and ensures that it completes its execution before it comes out. The scheduler or the operating system in the non-primitive type cannot take out the process from the processor unless it completes its execution. So we will talk about both of these primitive and non-primitive types and various algorithms that fall in each of these categories in this module. As we have discussed earlier, that when there are multiple processes waiting in the ready queue, the scheduler selects one of them based on a predefined criteria and passes it on to the CPU or the processor. Over here, the selection criteria for the scheduler is listed. The first one is the CPU utilization, which means that how much CPU is utilized, or how can we enhance the utilization of the CPU by the selection of any of the processes that are present in the ready queue. And the second one is the throughput, which is the number of processes that complete their execution per unit time. The next criterion is the turnaround time, that is the amount of time to execute or to complete the execution of a particular process. The next criterion is the waiting time, that is the amount of time a process has to wait in the ready queue. And then we have the response time. This is the amount of time that it takes from when the request is submitted and once we get the first response from the system. It is not the output but the first response from the system. This response time is usually calculated when we have time sharing systems, when we have multi programming environment where we have multiple processes running in parallel. Each process is actually demanding that they have less amount of response time from the system, and this time defines how responsive a system is. So the goals of an optimal scheduling algorithm is to maximize the CPU utilization, to maximize the throughput, to minimize the turnaround time, minimize the waiting time, as well as to minimize the response time for different processes present in the system. Over here we have different scheduling algorithms that we will discuss in this module. So as you can see that we have already categorized them in different classes according to the type of scheduling that they support. So you can see that we have some algorithms in the non-primitive class and that we have some algorithms in the primitive class. Just to recall the concept, non-primitive algorithms are the ones in which once a process goes into the processor, they remain in there unless they complete their execution, and they only come out once they complete their execution. On the other hand, in the primitive algorithm, once the time slice of the processor expires, we forcefully take out the process out of the processor and put it into the ready queue. So in the primitive algorithms, we have time slice dependence, and we take out processes forcefully. In the non-primitive one, we cannot enforce this time slice, and processes complete their execution whenever they get the processor. The first algorithm that we will discuss in this module is first come first served. As the name implies, the selection criteria of this algorithm is the arrival time of the processes. So all the processes are waiting in the ready queue, and this algorithm selects the process that arrived first in the ready queue. So based on the timestamp at which the process has entered the ready queue, this algorithm just picks that up and passes it on to the processor. Also, you know that it's a non-primitive type of algorithm, so uh, once a process gets the processor, it will remain in there unless it completes its execution. Over here we have an example of first come first served scheduling. As you can see that over here we have three processes, P1, P2, P3, and their order of arrival in the ready queue is P1 came first, followed by P2 and then P3. And the burst time, that the time these processes required to complete their execution are 24, 3 and 3 respectively. So P1 requires 24 seconds by the processor, while P2 requires 3 seconds, P3 requires 3 seconds as well. So the order of arrival of these processes is P1 followed by P2 followed by P3. So the Gantt chart that reflects how these processes will be in the processor will be like this, that from 0 to 24 we have P1 in the processor. As you can see that there is no time slice, as well as this is a non-primitive algorithm, which means that unless this P1 completes its execution, even though P2 and P3 are in the ready queue, still P1 will not be taken out of the processor. So once P1 completes its execution, it will be taken out and P2 will be allocated to the processor. And once P2 completes its execution, P3 will be allocated to the processor, and it will come out once it completes its execution. So this will be the Gantt chart of these processes having this bus time. So the waiting time for P1 is 0, as it arrived at time interval 0 and it is given to the processor at the same time. So the time interval for P1 will be 0 minus 0 equals 0. The waiting time for P2 is 24, as it arrived at time interval 0, but it got the processor at time 24. So 24 minus 0 is 24. Likewise, P3 arrived at time interval 0. However, it went into the processor at 27 times. So 27 minus 0 is 27. So these are the waiting times for these processes. And the average waiting time can be extracted by adding all three of them and then divided by 3, and you get the average waiting time for this particular scenario. So this average waiting time reflects how much a process has to wait on average before it can get into the processor. I hope that this concept is quite clear to you. So let's have a class exercise. So suppose that now the order of arrival of all of the three processes that we discussed in the previous example is like such. We have P2 came first in the ready queue, followed by P3, and then we have P1. The burst time requirements will remain the same. For P2 it was 3 seconds, for P3 it was 3 seconds as well, and for P1 it was 24 seconds. So please try to draw the Gantt chart for this exercise, and just pause your lecture for 10 minutes, complete that Gantt chart, and then calculate the average waiting time, and then please continue the lecture. So please stop it over here. Alright students, so you would have a similar Gantt chart where we have P2 entering the processor at time interval 0, and it came out at time interval 3, and then P3 enters the processor and it comes out at 6, and at this moment P1 enters the system and it comes out at time interval 30. So you should have a Gantt chart similar to this. You may have also concluded that the waiting time for P2 is 0 seconds, for P3 it is 3 seconds, for P1 it is 6 seconds. So I have placed all of these waiting times in here, and to get the average waiting time we will just add them and divide by the number of processes to get this value. So this is the average waiting time for this particular exercise. There is an interesting insight that I hope that most of you have already figured out. You can see that both of these exercises, we have same number of processes, their burst time requirements were the same. However, their average waiting time were entirely different. So in this case, the average waiting time is a lot better compared to the previous exercise. So this average waiting time, or the reduction in the average waiting time, is attributed just to the change in the order of these processes. This gives rise to an interesting phenomena that we call as convoy effect, which means that if we have a process having large burst time requirements, and if it enters the system and there are several small processes just waiting behind it, then the whole performance, or the average waiting time for the whole system, it can degrade dramatically. Over here we have a visualization of this convoy effect. As you can see that we have a longer job preceding various short jobs. So this convoy effect is a phenomenon that is present in first come first serve, in which the whole system slows down because of some slow processes. So in this convoy effect, we have some short processes that are following a long process, and this slows down the whole system. Now let's put some more richness to our exercises. So in this exercise over here, we have 5 processes from P1 to P5, and these are their burst time requirements. As you can see that over here we have an additional column that is the arrival time. So all of these processes, they are no longer entering the system at time interval 0, rather they have their arrival times. So P4 is arriving in the system at time interval 0. Then we have at time interval 1 we have P3. Then at time interval 2 we have P1. Then at time interval 4 we have P5. And then at time interval 5 we have P2. So now when we are making this Gantt chart, we have to ensure that at what time which process is already in the system, and then we will follow the order in which they have arrived in the system to be selected for the processor. So please take 10 minutes to solve this exercise. Please pause this lecture and come back once you have done it. Please draw a Gantt chart as well as calculate the average waiting time. So over here we have the Gantt chart. As you can see that at time interval 0 we have only P4 present in the ready queue, so this will go into the processor. As first come first serve is a non-primitive algorithm, so this P4 will remain in the processor unless it completes its job. So at time interval 3, the scheduler will again look into the ready queue to select the other process. Now we have 2 more processes in the ready queue, P3 that arrived at time interval 1 and P1 that arrived at time interval 2. However, as P3 arrived in the system earlier than P1, it will get the processor. So P3 will go into the processor at time interval 3 and it completes its execution, and it will remain in the processor for the next 8 seconds. And at time interval 11, the scheduler will again look into the ready queue to pick the next process. At this point in time, now the ready queue has 3 processes. First one is P1 that arrived at time interval 2. Then we have P5 that arrived at time interval 4. And then we have P2 that arrived at time interval 5. As P1 is the earliest process that came into the ready queue, the first come first served algorithm will pick P1. It will remain in the processor for the next 6 seconds, and at time interval 17, this P1 completes its execution. At that moment in the ready queue we have 2 more processes, P5 which arrived at time interval 4 and P2 that arrived at time interval 5. As P5 came earlier than P2, the scheduler will pick P5 and it will remain in the processor for the next 4 seconds to complete its execution. At time interval 21, we only have one process in the ready queue, and that is P2. So this will be selected, and at time interval 23, all of these 5 processes, they have completed their execution. So over here we have the waiting time for each of these processes. So first of all we have P4. So as you can see that it arrived at the system at time interval 0 and it get into the processor at time interval 0. So we have 0 minus 0 equals 0. So P4 has to wait for no time or 0 seconds to get the processor. So the waiting time for P4 is 0 seconds. For P3, it arrived in the system at time interval 1 and it get into the processor at time interval 3. So we have 3 minus 1, 2 seconds. P3 has to wait to get into the processor. So you see that P3 waiting time is 2 seconds. It arrived in the system at time interval 1 and it got the processor at time interval 3. So 3 minus 1 is 2. Next is P1. As you see that it arrived in the system at time interval 2 and it get into the processor at time interval 11. So 11 minus 2 is 9. So 9 seconds P1 has to wait before it get into the processor. The next one is P5. As you know that P5 arrived at the system at time interval 4 and it get into the processor at time interval 17. So 17 minus 4 is 13, which is the waiting time for P5. Now we have P2. So you know that P2 arrived at the system at time 5 and it get into the processor at time 21. So 21 minus 5 is the time that P2 waited in the ready queue. In order to calculate the average of all of these waiting times, what we can do is we can add all of their waiting times and then we can divide it by 5 to get the average waiting time. So the average waiting time for this scenario is 8 seconds. The main advantage of first come first serve scheduling algorithm is its simplicity. It is quite easy to understand and it is quite easy to implement. So this is one of the simplest CPU scheduling algorithms. Besides its simplicity, first come first serve also has some disadvantages. The first one is its non-primitive nature. As you already know that in non-primitive algorithms, once a process is allocated to the CPU, it remains in there unless it completes its execution. So due to this reason, first come first serve is not very efficient. It tends to have a higher average waiting time, and in the presence of multiple short processes behind one long process, the overall efficiency of the whole system goes down. And so due to this non-primitive nature, as well as the fact that one longer process can hold the execution of several short processes, uh, this is not an ideal candidate for systems where we have time sharing requirements or we have a good efficiency or responsiveness from the processes from the system to the user. So this is not an ideal candidate in such situations. So students, over here we will stop today's session. I hope you have understood everything that we discussed today. We started with the selection criteria of scheduling algorithms. Then we saw how an ideal CPU scheduling algorithm should behave. And then we discussed one very basic first come first serve scheduling algorithm, and then we saw how we can generate Gantt chart and how can we evaluate average waiting time for first come first serve. So from the next session we will start working on several different algorithms for scheduling. Thank you students, stay safe.